Yo, 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 Aiken, how you doing? I hope you're doing good, my friend. Let's go to the other screen here. Here we go. Hello, hey. Hey, long time no hear, Aiken. What you been doing up to, my friend? Hopefully you're doing well. Let me open up this tool here. What's up, my friend? What's up? What's up? What's up? Hopefully everything is going absolutely fantastic, my friend. Just been watching footy all day. What about you? Yeah, I've been kind of playing a little Final Fantasy. I've been kind of preparing my notes. Who's I watched the Denmark game yesterday. That was pretty good. Denmark Russia. It's a really emotional contest. That was pretty good. I've been watching a little bit of the Euros there. England's playing today. I saw, right. So unless they already have been playing. Yeah. We have the Czech Republic and England, Croatia and Scotland. Czech Republic's pretty good. Well, I think that I don't know. I think that I think England's got a pretty decent squad, in all honesty. So, I mean, I don't feel that they should have that much trouble against the Czech Republic. What? I don't know. I don't know what you think, Aiken. Who's gonna win? Who's gonna win the Euros? England need to draw or lose? Wait, Italy? Italy has looked really good. Wait, why does England need to draw or lose? Is it because of who they play after group stage? Are they trying to manipulate who their opponent's going to be? Well, that explains that then. France hasn't been playing all the Slovak. Well, yeah, you take the path of least resistance. Germany and France or Slovakia, Poland, third or random third team. Oh my gosh. So England is playing to draw and trying not to win their group. That's very rare to see. You're trying not to win. You think England can beat a team like France or Germany, or no? It's just not possible. Just put out your worst team. Put out the reserves, the substitutes. Put out a team like that. They can, but the you have so little faith, Aiken. Come on, man. Why do you have so little faith? You know, like it's like the World Cup all over again. The complete bottle jobs in the World Cup. You know. Look, Southgate should sub himself off and you lose. Look, yeah, if you wanted to lose, just go ahead and field 5 men on the field and take the 3-0 loss by forfeiture and walk away. that's that's what you should do. Just don't even bother showing up to the contest. I don't think it's allowed to use this. It has to be low key. I'm not sure how low key it can get when you're just staring at the standings. That's a little hard, to be perfectly honest with you. I gotta be low key, like, bro. That's a little hard. I don't expect him to put his best team out there if they're just aiming for second. They're aiming to play Slovakia or Poland. Yeah, they would want the better contest. Hey, Bernice, hello. Good morning / afternoon to you, Bernice. How are you? How we doing today? All right, my dude. Take this out here. All right. Why I have this in my pocket, I don't know. How we doing today, Bernice? We have hopefully you slept well, had a good time. Took a good days. Hopefully you're ready for some math. I hope so anyway. Woo-hoo. I'm doing absolutely fantastic, Bernice. I gotta ask you a question, Bernice. Let me ask you a question. Have you been able to follow the class so far? I want to know because again, obviously you've been going rather fast here the past 2.5 weeks, just burning through material like it's no tomorrow. So I hope that the material hasn't been too overwhelming. I know that in the summer semester it tends to be that way, but that's kind of a thing. So hopefully you've been able to, kind of get used to, the material. I hope you've been able to follow along. I guess that's the one thing I'm kind of worried about too. All right, getting used to it. Good. All right. I want to be sure that you're starting to get it. It's coming to you slowly but surely. Not. I know it's not too easy, but hopefully you've been able to get it. So again, if you're having any questions, please feel free to ask. Okay. It's been years since I've seen algebra. Fair enough. I mean, to be fair, it's been years since I've seen physics. So I understand your plight. My job is to make this transition as smooth as possible. As smooth as possible. All right? We all know math smells, okay? And math kind of sucks like that, but you know what? Let's try and make it as smooth as possible with the least amount of resistance. No, I'm too lazy to make it harder. That's my reasoning. I'm too lazy to make it super hard. I must have my breakdowns, little by little, piecemeal by piecemeal. It must happen. If it doesn't happen, then I will be sad. And me and math, man, go way back. Go to the way back machine, me and math. Let me check something here. Hey, Jess. Good morning / afternoon. How we doing? I hope we're doing absolutely fantastic there. Josie, hello. Good morning / afternoon. How we doing today? How we doing? All right. Got the gang hall here. All right. We're getting there. No, I started here a little bit late here today on the stream, but here we go. Chelsea, hello. Nicholas, hello. How we doing? Good morning / afternoon to you both. Hopefully you're doing absolutely fantastic. All right. We're about ready to get started here. Gonna get moving, and then we'll hopefully knock a couple sections out of the way. That's the plan. See what we can do. All right. Let's do it. Okay. All right. So let's do some intros, and then we'll go ahead and get going. All right, let's do it. Okay, let's get started today. Welcome back to Tuesday. All right, so today we're gonna pick up where we left off last time. Last time we talked about how to find zeros of polynomials. Okay, so we did about synthetic division. We did a lot of stuff with that. We looked at a ton of examples regarding that stuff there. So we got kind of used to doing synthetic division and again finding those zeros using the calculator and whatnot. Today we're going to be looking at not just polynomials, but we'll be looking at one more type of function here, a function that we've already seen before. But we're going to be looking at it in a slightly different view. Not a totally different view, but a slightly, just a smidge, slightly different view. Okay. So let's go ahead and take a look at that here. And let me that page. Okay, hang on a second. What do I have the page? All right, there it is. All right. So let's go to the big board here. So today we're going to be doing sections 3.5 and 3.6. That is the plan. Let's go to the big board. All right. So this is the last handout for chapter 3, which is 3.5, 3.6, 3.7. All right. So that is the here. Just to give you a heads up here, by the way, I will be posting a test here for chapter 3 here later this week. I'm still in the process of making it up, but again, it will be made up here for the chapter 3 test, and then it'll be set and ready to go for you guys to go ahead and give it a try. So let me get to the proper page. Thought I found the page. Back. Oh, okay. That's fine. All right. Good stuff. All right. So today, let's go ahead and focus on the first question here. We're gonna blow by a bunch of questions kind of all at once here, so you can kind of follow along here carefully. All right, and we'll go through it. All right, so let's look at question 1 here. What are rational functions? Okay, so I'm going to zoom in on this one here just for on purpose here for just a second. So a rational function here is a function of the form f of x is equal to n of x over d of x. Now I'm going to be referencing these quite often here on this handout. So again, just as a reminder here, n of x is the numerator function. All right. And d of x here is the denominator function. So I just put the letter there so that way it's easier to kind of recognize. Denominator function. That in chat. If I can spell, let me know. But it's not happening today. All right. All right, so I'm going to reference numerator function and denominator function quite often here in order for us to put together some certain pieces of a rational function. But again, what do these rational functions look like? Again, it's one function on top of another. Fairly straightforward. Again, if you want to use the paint tool here, again, it would be, say, something like x plus 3 over x minus 9. All right, so this is a rational function, one function on top of another function, and then we're just going to go ahead and explore whatever we do with it. Okay, that's essentially what we're at. All right. Anyway, moving on. What we're going to do here specifically is we're going to want to go ahead and graph these rational functions. So we're going to look at properties here of these rational functions. And we're going to want to graph these rational functions, okay? So that's the whole point about what we're going to be doing here today. Now, some of these next questions here will give a nice reminder about what we talked about in the past, but it's starting to put the pieces together here. Once we put the pieces together, then putting the graph together ain't so bad. So, yeah, there's that. Magic, it happens. All right, so it's also a card game. Anyway, let's look at question number 2. Question 2 says, how do we find the y-intercept? All right, so the y-intercept here is we're going to set x is equal to 0 and solve for y in the function. And that's all you're going to do. If you recall here, that's all we need to do for the y-intercept. Plop in 0 for x and then see what you get out for y. So just put in 0 in the function, and then that's all you need to do. So trick here, just plug in 0 into the function for x and solve. That's it. Not much to it. So again, 0 comma 6 or 0 comma minus 2 would be examples of a y-intercept. Okay, x-intercepts. How do we find x-intercepts? Again, the basic premise of solving for an x-intercept or intercepts, again, depending on the equation we're given, is, or function, either way, set y is equal to 0 and solve for x for the function. So we've seen x-intercepts before already. We set, again, all x-intercepts are of the form x comma 0. We have 5 comma 0 minus 3 comma 0. Again, the trick here, though, okay, so what's the trick here? So this is kind of important for this one. So I do want to actually reference this guy. The trick here is to set the numerator function equal to 0 and solve for x. If we want to find the x-intercepts here, we need to set the numerator function here equal to 0. Now, I am being very specific about the numerator function. Is the reason why we don't set the denominator equal to 0 is because we cannot divide by 0. Okay, we're going to get another result with the denominator being 0, but we can't divide by 0. So the denominator being 0 is going to be a bad time for us if we want to find x-intercepts. But that numerator, if set it equals 0, see what we get, right? And then those will be our x-intercept or intercepts, whatever the case may be. All right, and we'll look at an example of that here, but just need to go through a few of these guys here. Okay. All right, so all right, let's see. Yeah, all right, that'll be fine. Okay, now the most important part here, in my estimation, is what's here on the right-hand side of the screen. So I'm gonna make this. I'm gonna move my face away here for just a moment so you can see the notes here. So, all right. So let me go ahead and take my face away here for a moment, and let's look at question number 4. Hey, Moss, thank you for the follow. Appreciate that, my dude. It says, how do we find vertical asymptotes? Okay, so let me go ahead and define one thing here about asymptotes. All right. Good to see you, Moss. Welcome, welcome. All right, so asymptotes by itself, at least the base definition, are lines, specifically imaginary lines. The graph gets close to, but doesn't quite touch. So, hey, Gomesh, how you doing? All right. So that's what asymptotes are on the basic, and what we're going to want to find is we're going to find two types of asymptotes, or technically there are 3 types of asymptotes, as you can see here on the screen, but we'll talk about that here in just a second. The first one here are vertical asymptotes. Okay, vertical asymptotes, again, if we just look at a basic picture here, is just going to be a vertical dotted line. All right, I'm doing great, my friend. Oh, all vertical asymptotes can be found by setting the denominator function d of x equal to 0 and solving for x. Now, the reason why this is going to occur specifically is because, again, vertical asymptotes are where again, the graph is not going to exist. Essentially, if we find out where the denominator is equal to 0, all right, then it's going to get closer and closer to that value, but it's not going to quite touch at that particular value because we have that 0 actually occurs there. I did put a little note here as well. So let's go ahead and note. It says here, if the function can be simplified by canceling out a term on the numerator and denominator, do that before you find the vertical asymptote. All right. Good luck. Thanks. Thanks for the good luck. I appreciate that. I'm not sure what you wrote there for the other stuff, but okay. Um, all right. So let's see what we have here. So again, you have to simplify before you cancel out the terms here on the numerator and denominator before you find the vertical uh the vertical asymptote here. All right. Okay. Okay, so let's take a look at number 5 here, right? I don't speak Thai, Moss. Although I respect, though I have a friend who's married to a Thai woman. She's very nice. Good friends. Very, very friendly country. Had my mom and sister go out there. Had a great time. So let's take a look here at number 5. I need to get through these questions here, and then I can do example. All right, so let me do number 5 here really quick here. So how do we find horizontal asymptotes? So for horizontal asymptotes, we're going to have two cases. All right. So if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote will be equal to the leading coefficients of the numerator and denominator divided by each other. And if the degree of the denominator is bigger than the degree of the numerator, then the horizontal asymptote is y equals 0. All right. You know what? Here's what I'm going to do. I got an idea. I have an idea. All right. So this is a lot of information. I ain't going to lie. A ton of information. Okay. One thing I would suggest to do is, again, just take a screenshot or whatever, right, of what you see here on the screen. We're going to go through each part here carefully. That way we can highlight each one of these questions here. I'm going to showcase number 6 here as well um, in just a little bit. But let's just start off with something easy. Let's just work our way down after that, okay? All right. Okay. All right. So just let me know. Let me know when you have let me know when you have a screenshot there or you have your notes written down, and then I'll move forward. Just type just type done in the chat or all good in the chat, and then I'll move forward once you guys have that down. I'm gonna go through this very carefully because I know I'm kind of speaking too much here. So nah, that's okay. That's okay, Nicholas. I know there's always a delay. So I know there's like a delay of like a few seconds to like maybe 10 seconds for some people. If you have like a long delay, then just refresh your stream, and then hopefully the delay will pick up again. So just let me know here once you guys are ready to go. See some of you, but others who are lurking in the chat, go ahead and just tell me if you got it or not. Done. Okay. So I'm going to move forward here. All right. All right. Good. Good. Okay. Let's go back to the main screen here. All right. So I'm gonna basically kind of switch back and forth to this, and then we're gonna see how this works. All right. Okie dokes. So let's do a function here, and let's see what we got. All right. Easy peasy. Canvas size. All right. So the first example we're going to do here, we're going to go ahead and follow the steps here. We're going to put this graph together. Again, we want to get the key pieces of information here first. So let's start off with something nice here that isn't like super over. All right, let's go with this. It's actually pretty decent. Is that x? Oh, that should be plus 2. All right. Okay. So here we have x plus 2 over x squared plus x minus 6. All right. And so what we're going to do here is we're going to first figure out, we're going to go each step one step at a time here. And we're going to start putting the pieces together into basically graphing this particular rational function. I'm going to quickly go back to the handout here for just a moment, because as you'll notice here on the handout is how do we graph rational functions, which is question 7. We're just going to go ahead and do the steps here. So the first step here is to do find the x and y intercepts, okay? So that's what we're going to do first. So just one step at a time here. We'll go slow. All right, so the first thing is let's find the x and y intercept. Let's do the y intercept first, which is the easiest of of the processes. Again, we're just going to set x is equal to 0 here. So we're just going to put 0. We're going to find f of 0. So it's going to plug in 0 into our function. And then in this case here, we get 0 plus 2, that's 2. And we get this over negative 6. So putting this down here, we get negative 1/3. So here we have a 0 comma negative 1/3. All right, there we go. That's going to be our y-intercept. All right, so far we already have 1 point on the board. Seems fair. All right, pretty easy, pretty straightforward. All right, not so bad. All right, let's go over the next part here. Okay, next part here is let's do the x-intercepts. Okay, so for the x-intercept here, we're going to set the numerator function here equal to 0 and solve for x. Okay, so just the numerator. All right, so not the denominator, just the numerator here. So the numerator here is x plus 2. So we're going to have x plus 2 equals 0. Subtract 2 on both sides. Seems pretty simple. All right, so x is equal to negative 2. So here we have another point here at negative 2 comma 0. All right, so before we move forward here, are there any questions about that? Hopefully that part there, super simple, very easy to do. All right. All right, very good. Okay, so that shouldn't be too much of a problem. I think we're okay there. Let's focus on the next part at hand. We have 2 solid points there. Good stuff. Let's go back to the handout here and talk about the next part. Okay. The next part here is to find the vertical asymptotes. Okay. What happens if you use the denominator? Bad things. We use the denominator in the next step over though, Jess. So in step 2 here, we're going to use the denominator function. So I'm being very specific here. First step for x-intercepts, got to use the numerator function for the x-intercepts. Denominator function we're going to use in the next step over, okay, which says to find the vertical asymptotes by setting the denominator equal to 0 after you simplify. So some cases, some problems, you may have something that's easily simplifiable that you can cancel out terms. So let me go ahead and I stated it up here. So I said here, if the function can be simplified by canceling out a term on the numerator and denominator, do that before you find your vertical asymptotes. Okay, so if you can factor stuff out and cancel stuff out, because some problems may be thrown your way where that's possible, do that before you find your vertical asymptotes. Okay, before you find your denominator equal to 0. So that's kind of a little side note there that is important, is to see if you can simplify. All right. Now, in this case here, let's go back to our example. In this case here, we can simplify a little bit. Let's see if we can cancel anything out first. What can, actually, what does x, that's actually, I don't know why I'm writing this here. What does x squared plus x minus 6, what does that simplify to? Can we factor that out? And if we can, what does that factor to? X squared plus x minus 6. What does that factor to if it does factor? Okay, great. That's right, Stephen. All right, Nicholas got it too. So this will be x plus 3x minus 2. So if you notice here for this, we can see if things cancel out. Now we have x plus 2 on the numerator, so unfortunately we cannot cancel anything out. But this does help us out considerably. Again, we set the denominator equal to 0 here, even though we are not able to go ahead and cancel stuff out, unfortunately. Too bad, so sad. But we still set this denominator equal to 0, and we have already found out what it factors to here, leading us to pretty nice conclusions here at the very least, is that we're going to get two vertical asymptotes here. Our first vertical asymptote here is going to be x is equal to -3, and our other vertical asymptote here is x is equal to 2. So we're going to have two vertical asymptotes here because those are the two zeros of the denominator. All right? Any questions about that? So just taking it one step at a time. All right? We're not doing anything super fancy, not doing anything brand new. It's just one step at a time. Okay, so I'll move forward here. All right. So what's the next step here? Now the next step here is going to be a little bit interesting here in step 3. Go back to the handout here for just a moment. Step 3 says to find the horizontal asymptote or the slant asymptote. Now let's talk about that here for just a moment. All right. So I'm just going to expand upon this and we'll come back to the example here. So let's look at number 5 one more time. How do we find the horizontal asymptote? Well, what we need to do here, horizontal or slant asymptote, what we need to do here specifically is we need to look at the degrees of both the numerator and denominator. Okay, so that's the goal here. If we look at the degrees of both the numerator and denominator, then we can go ahead and see exactly what the story is about which one that we're going to fall into. As again, if you see here, the horizontal asymptote will occur as if the degrees are equal or if the degree of the denominator is bigger than the degree of the numerator. We'll get a slant asymptote as if the degree of the numerator is one more degree than the degree of the denominator. Feels kind of weird, but it's just how things work out for asymptotes in this case. Now, probably the most important thing that I could probably highlight though is this part right here. Probably the most important note, and this is why we have to check the degrees first, is that you cannot have both a horizontal asymptote and a slant asymptote. So either get the horizontal asymptote and then that's it, or a slant asymptote and then that's it. All right, so you can't have both at the same time. That's not how it works. Okay, I'm just going to point that out here that you either get one or the other, but not both. Okay, now let's take a look at our case here. Let's take a look here at the degree. Let's take a look at the degree of the numerator. What's the degree of the numerator here? And we'll take the degree of the denominator as well. What's the degree of the numerator function? 1. Okay, that's correct. The answer is definitely 1, right? Because we have x to the first here. Okay, good, good. What's the degree of the denominator? Degree of the denominator. All right, pretty solid. 3? I think you mean 2 here. 2 is the highest power in the denominator there, Josie. If the denominator doesn't factor, what do you do in that case? Well, try and use a quadratic formula if it does factor into something with, something strange. If it turns out to be like imaginary numbers, then it doesn't have any asymptotes, any vertical asymptotes. That can easily happen there, Jess. And that's a fair question. 2 because of x squared, yes, yes, Stephen, that's correct. So 2 because of this x squared here being the largest power. Remember, degree is the largest power, largest powered term in the polynomial. combined power really, but really largest power term in these cases. So we're going to keep these simple. I promise you that. All the examples that you're going to see are going to be fairly simple. So, okay. Okay, so as you can see here, um, we have the degree of the denominator is bigger than the degree of the numerator. Okay. So because the degree of the denominator is bigger than the degree of the numerator, let's go back to our notes. So if the degree of the denominator is bigger than the degree of the numerator, then the horizontal asymptote is always y is equal to 0. So y is equal to 0 is going to be our horizontal asymptote here, in this instance. Okay, cool. All right. Again, once we find a horizontal asymptote, that's it. Okay. So that's all you can do. All right. No slant asymptotes, no nothing. All right. That's going to be step number 3. Any questions about that? All right. All right. So this process here is actually relatively fast, even though there's a lot of information on the screen, surprisingly enough. Um, let's go ahead and take a look back at our notes here for the next step. Step number 4 is to find some points between each vertical asymptote and map it out using the calculator. And then we can go ahead and graph it as our last function, as the last thing we need to do. So let's go ahead and at least do a preliminary graph. We can do that because we do have some pieces of information that we can easily put on a graph, right? So we're going to take out the calculator here to kind of make it a little bit more clear. But at the very least, we can go ahead and see what we're working with here. So, all right, let's take out the calculator. Right. While that loads up, go ahead and take a look at a graph here. So we do have 2 points. We have 0 comma negative 1/3, and we have negative 2 comma 0. So we're going to go ahead and map both of those out first. So let's go ahead and put that on. 0 comma negative 1/3 is like, I don't know, tough to put maybe right here-ish. And what we have here, negative 2 comma 0. Okay, so right here. All right. We also have 2 vertical asymptotes at x is equal to -3 and x is equal to 2. Now, what do those look like? Well, at x is equal to -3, we're going to have a dotted line going vertically down. Okay, so this is what the asymptote is going to look like here. Visually, that's what it looks like. We're also going to do the same thing here at x is equal to 2. Go ahead and put that down just like so. We also have a horizontal asymptote at y is equal to 0. So that's just directly over here. Okay, so this is what we have here so far for our asymptotes that we had found here in steps 2 and steps 3. Okay. Okay. All right. Let's take out the calculator here. And now let's go ahead and graph this guy. Okay. So we're going to plug in the original function into the calculator, which was this. So go to y equals here. Clear this out. Again, put this in parentheses. You'll need to put this in parentheses, otherwise the calculator will do the wrong graph for you. So x squared plus x 6. Okay, and let's take a look at the graph here. Graph is going to look, there it is. Okay, now if you have the super old school calculator, it actually draws in, it actually puts in the asymptote in there because it was kind of made that way. But if you don't have it that way, that's fine. If you have it like this, then that's the new school way. Okay. So before we move forward here, I want to be sure that everybody kind of got this graph on their calculator. Type done in the chat if you got this graph on your calculator to work out. If I went too fast, just let me know. What do just in case if your range is, just in case if Brian, if your thing is kind of out of whack, just hit the zoom key and then go to like zoom standard number 6, and then it'll reset your range there. So it'll you can go ahead and do that if everything's kind of out of whack. Yeah. Yeah, no problem. So go ahead and type done in chat if you have this graph that appears on your calculator here. Again, you better make sure you put parentheses, guys. You can't skip. All right. If you got an error range, Josie, like again, this is what you should have for y equals. And again, if you have an error range, hit the zoom key and go to number 6, which is zoom standard, and then hit enter, and that'll reset your ranges. Got it now? Josie, did you hit the zoom key and go to number 6? Make sure that you got there. Let me know if everybody else has got it here. Okay. 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 So did you hit the zoom key? So did you hit the zoom key and go to number 6? Okay. You want to reset your range on your calculator there, okay? Hit the zoom key, go to number 6 and hit enter. Cool. All right. Excellent. All right. So, what do we want to get out of this particular guy here on the calculator? So if everybody got it here, let's go ahead and move forward here. What do we want to get out of this particular guy here on the calculator? So what we want to do is we just want to grab a few points here. It doesn't have to be super perfect, okay? Again, we can get some general points and then put it on a graph. And then we're going to make a general graph here. Again, that's all we're really looking for here in this particular case. So if you want to go ahead and you can go to the table there, or you can go ahead and hit the trace key. The trace key there, you'll see a few things. 0, comma, -1/3, we have that already, but we can take a look at some other points. We can take a look at some of the key points here, like maybe this point right here is like -2.7 and -2.73 and 0.56. So let's go ahead and put that in here. Hey, probably saying, why am I taking these specific points? Well, I'm taking these specific points just to help me shape the graph. So they're not like I'm going to. They're not like, oh, they kind of do come from out of nowhere. I'm not gonna lie, but I'm just taking these points here specifically just to shape the graph into something doable. It's not an exact science for this last part, so I'm not expecting you to make it an exact science either. So do understand that it's not intended to be that way. So what would I do for these last 2 points? I could pick a point here, 2.73 and 1.13. Okay, and let me pick a point here on the last one. I'm just writing these down as I just kind of graphing them. Here we go. Negative 3 1/3 and 3/4. So is that negative 10 thirds? Go ahead and paraphrase here. Negative 10 thirds. You could write the decimal here. I wouldn't care. I'm just writing the fractional equivalent, but whatever. Doesn't matter. So okay, I plot these points here. Okay, as best as possible. Like I said, we're not going for exact science with these graphs. Okay, it's impossible to do when you're doing decimals. All right, so if you're, don't worry about don't worry about it. We're gonna let the essentially, if you're gonna graph it on the uh you're gonna graph it on the computer, really it's gonna do pretty much most of the work for you. You just have to find some points that'll be that'll satisfy it pretty much. So let's see here. We have this. Here's a good point here. 2.73, 1.13. So that's roughly about here-ish. Okay, and then we have negative 2.73, 0.56. So that's right about here-ish. And we have last one here, which is, what is this, 1.06 and 0.8. All right, so right about here. All right, so I'm just ballpark estimating these. Okay, so we're not, like I said, not dealing with exact sciences here. But what does this graph look like if I want to make it look like it has on the calculator? Here we go. Make it look somewhat respectable. All right, there we go. And again, the asymptotes, remember, the asymptotes are just where the graph gets close to but doesn't quite touch. Okay, so you can see how it happens that these end where these lines go really, really close to, but again, don't quite touch. These asymptotes serve as like little boundary levels. Okay, and there we go. We have a graph for our rational function. Okay, any questions about that? I'm guessing, I don't think so. I think they're just going to give you like the graphs and just ask you to match it, probably. But if they ask you to go ahead and graph it, then at least you'll know how to find the points. I think so, if I recall correctly. So, but hey, that's why we have the calculator here to help ourselves out. So that's okay. No worries. Um, any other questions before we move forward? No thanks. Okay. No. All right. Let's move forward then. Okay. Next. All right. So we're gonna move forward here. All right. So let's do another example for this, and I need to make up another example. So let's do that. I'm gonna take a look at a couple of cases here. Just a couple more cases in that. Okay. So now that we have that all kind of explained through, these problems here go by rather quick. So okay, which one I want to do next? Which one doesn't absolutely smell? Alright. That one doesn't smell. That's fine. I guess. Yeah, that's fine. Okay. So here we have 3x squared plus x minus 4 and over 2x squared minus 5x. All right. So what we want to do here is we want to go ahead specifically and we want to see exactly, some of the graph behavior, the y-intercepts, and put together a graph. And it's not as bad as you may think. Let's go through each step here. All right, step 1 here, we'll find our x and y-intercepts. All right, see if we can find any. Let's try the y-intercept first. You plop in 0, and we get 3 times 0 plus 0 squared, sorry, plus 0 minus 4 over 2 times 0 squared minus 5 times 0. And we're kind of out of luck here because we get minus 4 over 0. So there is, in this case here, there will be no y-intercept, okay? So no y-intercept. And that's plausible, okay? So understand that sometimes some functions are just not going to have a y-intercept. X-intercept. Okay. For the x-intercept, we're going to set the numerator here equal to 0. So again, we're going to have 3x squared plus x minus 4 equals 0. Okay. Now, you could factor this out using the AC method or the quadratic formula. Quadratic formula is going to take you a while. Let's see, what is this factor to here? So two numbers that multiply to minus 12 and add up to 1. So that's going to be 3 and minus 4, or 4 and minus 3, I should say. So I could split this up here. If I do this out, let me do that really quick. Minus 3x plus 4x. 4. Okay, so become 3x, x minus 1, 4 times x minus 1. Okay. So again, I'm just using the AC method here, but I know I'm kind of skipping ahead a little bit. So for the sake of time, I'm kind of skipping ahead, so apologies about that. So if you factor it out, you get 3x plus 4 times x minus 1 is equal to 0. So here we're going to get two values for x here. We have x is equal to negative 4/3, and x is equal to 1. So we have two x-intercepts going on here, negative 4/3, comma 0, and 1, comma 0. Okay, so those are our two x-intercepts that we have here in this case. Okay, that's step 1. All right, step 2 here, we're going to find the vertical asymptotes. All right, so let me ask this question here. How do we find the vertical asymptotes? What do we do? How do we find the vertical asymptotes? How do we find the vertical asymptotes? What do we do? Set the denominator equal to 0. Okay, good. That's right. Let's set 2x squared minus 5x equal to 0. All right. let's go ahead and solve for x. What should I do first? How do I solve for x? I can't really add 5 in this case, Brian, because I have 5x. I guess. Well, crap, man. It'll make it a bit easier, I promise. All right, so how do we solve for x here? We have 2x squared minus 5x equals 0. How am I going to solve for the values of x that make that true? Factor. Factor what? I say factor, I said great. I agree. Factor what? An x. Okay. I like that idea. Just factor an x. Yeah, factor an x out. All right, so if I factor an x out, okay, what do I have left over? All right, 2x minus 5. Perfect. All right. So what are my two vertical asymptotes? What values for x do I get here for my vertical asymptotes? Tell me what we get for our vertical asymptotes. 0 and 5 halves. That sounds like a plan. Yes. Perfect. All right. We know exactly where we're going to put those vertical asymptotes. All right. Excellent. Let's do step 3. All right. So step 3 here is now we're going to find the horizontal or slant asymptote. So let's go back to the notes here for just a second. And again, we just have to compare the degrees of both the numerator and denominator, and we're going to find out which one of these two cases we're going to have here. How do we get 5 halves? That 2x minus 5 is equal to 0 here, Bernice. Add 5 to both sides. And we get 2x is equal to 5, and divide by 2 on both sides. Uh-oh. Well, it would be helpful if you could see that. Hang on. My bad. Hang on. Kind of being blinded by the bar there. My bad. So that's how we get x is equal to 5 halves. All right. No problem. Okay. So going back to the notes. Oh, I clicked the wrong thing. Bye. Hang on a sec. Okay, here are the notes. Here are the notes, Brian. Just take a quick picture here because I need to go back to the example here. Okay. Cool. All right. Now, step 3 here. Let's find if we have a horizontal or slant asymptote. So we're going to take a look at the degree of the numerator and the degree of the denominator. What is the degree of the numerator? What's the degree of the numerator? 2. That's right. What's the degree of the denominator? Degree of the denominator is 2. Okay, that is correct. They are both 2. All right, 100% correct. So, if we specifically look at that, let's take a look back at our notes here. If the degree of the numerator is equal to the degree of the denominator, what we're going to have is we're going to have a horizontal asymptote. Okay? So, actually, you know what I should have put? Probably would have been easier if I did this, because I'm a dope. Fine. All right, so if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote will be equal to the leading coefficients of the numerator and denominator divided by each other. So essentially what this means in this example is if I want to find the horizontal asymptote, okay, I just take the leading coefficient of each respective guy. So essentially this is the leading coefficient 3 because that's in front of the highest power of x squared. And this is the leading coefficient of the denominator, which is 2 because that's the number in front of x squared as well. So our horizontal asymptote here specifically is going to be y is equal to 3/2. Okay. So that's what we have here for that. Okay. All right. Okay, so again, taking each of these leading coefficients, that's how we're going to find the horizontal asymptote if these two guys are equal. Okay. That's only if they are equal to each other in degree. No other case is that happening. All right. All right. So if we put this graph together, let's put a simple graph here together. We have a few guys here. First of all, we have vertical asymptotes at 0 and 5/2. So here's our first vertical asymptote at 0. 5/2 is 2.5. So I'm going to have a vertical asymptote here. Not so vertical, but there you go. Yeah. It looks pretty ugly. Let's get rid of that curve. All right. Okay. Next, we're gonna have a horizontal asymptote here, also at positive 3/2, so 1.5. Okay. And we also have some points here. So let's go ahead and put in those points that we have here. We don't have a y-intercept, unfortunately, so that's out. But we do have two x-intercepts here, one at 1, 0. We'll mark there. And at -4/3, 0, so just a touch below 1. There we go. And now we just go ahead and put this on a calculator. Let's just see what we get here. And that'll be our graph for that. So let us take a look here at the calculator. Actually, make it a tad smaller. Back here for a second. There's the original guy. Okay, so let's put in the function here. Get 3x squared plus x minus 4, that in parentheses, divided by 2x squared minus 5x. Okay, we'll go ahead and graph it. All right, so we can see what this graph generically looks like. All right, so I know it's not the most greatest thing ever, but well, there it is. Okay, so we already have some points here that we can generically put out. Let's just find a point for that last part, that rightmost graph there. Let's hit the trace to see whatever that is. I don't know what that is. Let's pick a random point here. So 4.09 and 3.86. All right, fine. So I'm just going to randomly pick a point here just to plop on the graph so I can get a generic shape for that last last curve. So let's see here, 1, 2, 3, 4, 3.86. Right about here. Fine. All right. Again, not an exact science here, but it is what it is. All right, so here we have a curve here that we can clearly see what's going on. Again, this is just a generic drawing of the graph. Again, we're not dealing with exact sciences here in terms of the graph. So this one curves up just like so. This one here kind of goes pretty smooth up here, and kind of goes pretty smooth down here. There you go. And then this one here goes down much right away and kind of tails off this way. So, all right. And there we go. We have a graph that is easily put together. All right. Again, the last part here, like I said, not super exact for what we want, but you can see how we could put it together. All right. Questions about that? Okay. So we have one more example to do here for this specific one, for this specific section, and then we'll move on to the next one. So I'm not going to do the graphing for this one here, so this one here will go by even quicker. I only want to do one specific part of the process, just to kind of showcase one thing. We'll do that. Okay. Yeah, that's fine. Okay, so let's say we have this, okay, for example. All right. And you were asked, okay, what do we do with this here? How do we figure out the other thing that I guess I need to talk about here is I guess what I'm trying to say is, what about slant asymptotes? So there's one case where you can get a slant asymptote here, and that only occurs if the degree of the numerator is one more than the degree of the denominator. All right, and basically all you got to do is do long division and ignore the remainder here if you're going to get a slant asymptote. So I'm just going to skip to that part there. If we say, okay, if we want the degree of the numerator here, the degree of the numerator here is 2, and the degree of the denominator here is going to be 1. So the degree of the numerator is bigger than the degree of the denominator by 1. So in this case here, we're going to get a slant asymptote. And in order to get that slant asymptote, we just do long division with this. Now I know, admittingly, you could do synthetic division with this, but some cases will divide by x squared or whatever. So I just want to keep it consistent. So all we're going to do is do long division like we did before in the previous couple sections ago. So again, we're going to just get x here. What times x equals x squared? Well, that's just x. So here we get x squared. We get x times x minus 3. So here we get x squared, x times 3, get minus 3x. Again, we change the signs here. Go ahead and add these together. This cancels out. Get x plus 3x, that's 4x. Bring down the minus 6. What times x equals 4x? Well, that's going to be plus 4. So then you have 4 times x minus 3. So here you get 4x minus 12. Okay. And again, just change the signs. Da 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 da. Okay. Cancels. Leaves you with 6. All right. Now, what I want to point out here specifically in regards to this quick example is that in this case here, if we go back to our notes, we're going to go ahead and ignore the remainder. Okay, so you're going to go ahead and ignore the remainder. You don't care about the remainder here. So I know I did this out here and stuff, but again, 6 here has no relevance into finding out what the slant asymptote is. The only thing we care about here is this guy up top. This is our slant asymptote. Okay, so our slant asymptote here is y is equal to x plus 4. And then you would literally draw the asymptote of the equation x plus 4 on your guy. And then that would be the slant asymptote in this case. Again, because we found a slant asymptote here in this case, then what that means is that there's no horizontal asymptote. Okay, remember, you get one or the other, but not both. Okay, so I just wanted to point that out there about exactly what we get here for the slant asymptote case, so that way you'll know how to attack those if you see those. All right. All right, questions about that one? Okay. Let's see here. Do I want to do that? Is the question. And the answer is yes, I do. All right. All righty. So that, in a nutshell, is pretty much all of section 3.5. Okay. So now that we have that out of the way, we're going to move to section 3.6. All right. Blink says to hydrate. Thanks, Blink. Thank you. Okay. So what we want to do next here is let's move on to the next section here, which is in the same handout. We're now going to go to question number 8, and let's see what we get here. So I'm actually going to move this around. Give me a second here. Something. I like to keep all my problems on the same page, all my questions. So question 7. How do we? Not question 7. Question 8. Pardon me. What are polynomial and rational inequalities? So that's what we're going to be looking at here in this next section, 3.6. Polynomial and rational functions here that are going to contain inequalities such as less than or equal to, bigger than or equal to, less than, strictly bigger than. All right, fine. Okay. Now, let me move my face. So let me move this away here for just a. I wanted to not do that. All right. So let me move this here. All right. So let's answer question 9. Question 9 says, how do we solve for polynomial inequalities? Now, let me give you guys a, again, if you want to write this down or have a screenshot here, let's go ahead and take a minute and you guys can take a screenshot or write this down. Here is our step-by-step process here about how we can go ahead and solve for polynomial inequalities. Now, typically when I usually teach this particular lesson, I like to go through this not just by steps by stating it, but I like to do an example in conjunction with these steps here because it's a lot easier to kind of visualize. But let me give you guys a minute here to write this down so that way, or again, screenshot it here so that way you can kind of follow along with what I'm going to be doing here for the examples. Because I'd prefer to do more examples than kind of just stating stuff back and forth all the time. So like state everything at once and then do it like it's a pain. So let me know when you guys are done and then I can move forward to doing an example. Done. Okay. Wait for some other people to get done here. Again, type done in the chat once you have these notes all set and ready to go, and we'll get started with the examples here. All right. Hopefully everybody else is good here. Danny, E-Man. Hopefully you guys are okay. Fritz. Might still be right. E-Man, yep, okay. 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 Danny, you okay? Hopefully Danny's got it. Take just another minute here. I know it's a lot to write down sometimes. Short thing. All right. Okay. If you don't have this down again, just reference back to this video here. It'll be up for a while, I guess. All right, so I'm going to put this on the side here because I need to do a practical example here with this. And we're going to follow the steps here, as you see here on the left, with our example on the right. Okay, so that is what we're going to be doing here next. Okay, so the first one here that we're going to be doing is a polynomial inequality. All right, and let's go through this one step at a time. One of the things that'll be very helpful for this in actuality is, again, we're going to rephrase the problem, and then we're going to visualize the problem here to make it even easier for us to actually solve for. All right, so the example that we'll do here specifically is... Let's see which one I want to do. That's not the one I want to do. All right, that's a good one I want to do. All right, let's do this one here. This is specifically a problem from the book, but it'll showcase a few of the things that we'll need to encounter, so I don't have a problem with that. Okay, so here we have 5x is going to be less than or equal to 2 minus 3x squared. Okay, so this is what we have here in this particular case, all right? Now, what we want to do here specifically is let's go through each of the steps here and find out how we can solve for x in this inequality in order to get this down. Okay, step one. Step one here is to move everything over to one side so the inequality has 0 on one side, if necessary. Now, this is definitely necessary here in this case, as we do have x guys on both sides of the equation. Not the most ideal thing to do. Now, what I'm going to do here seems a little unusual, but I'm going to make sure that I'm going to move the 3x squared and the minus 2 over to the left-hand side here. Now, you're probably saying, well, why are you going ahead and doing that? You know, because we're going to get 3x squared plus 5x minus 2 is less than or equal to 0. And you're probably wondering, why are you going to do that specifically? The big reason that I'm going to do that is, well, it's first of all, I think a lot of people say 0 being on the right side is easier. Secondly, is I want the number for x squared to be positive. So the coefficient for x squared should be positive here. So I'll put it as a note here. Note, I want to keep the number in front of x squared to be positive. Now, the reason why I want to keep this as positive is because it's a lot easier for me to manipulate using a lot of the rules that we've talked about before, like factoring and whatever. So with negative, it tends to get a little bit more messy, so I don't want to do that necessarily all the time. Okay, so this is what we went ahead and did here for step number 1, is just shuffle stuff around. All right. Let's get into step 2. Okay. So step 2 says, take a look at what step 2 says. It says change the inequality sign to an equals. All right? Good. That's all we want to do here. That's its own separate step. You're probably saying, "Wow, that seems really, really silly to do." One of the things that I like to do is to break down the steps in terms of importance. Sometimes something as subtle as that, it changes the entire thing. Again, I'm changing just the slight context of the problem here from inequality into equals to make this a little bit easier to digest. So making sure we remember to do that, I put that as a separate step. Okay. Step 3. Find all the zeros of the polynomial. Okay, so now that's what essentially we want to do here, is find all the zeros of the polynomial. In this case here, we could go ahead and do the AC method if we wanted to. Again, we want to find, in this case here, to factor this, two numbers that multiply to -6 and add up to +5. So we're going to have 6 and -1 to be our two numbers. So we're just going to change that over. 3x squared plus 6x minus 1x minus 2 equals 0. Just going to factor these groups. 3x, we get x plus 2. Bring down this minus. Here we can factor out a 1, and we get x plus 2 again. If I'm going too fast, let me know. Okay. And so here we get 3x minus 1 and x plus 2. So our two x values that we're going to get here that make this 0 is going to be positive 1/3 and negative 2. All right, so let me stop there for just a second. Apologies. No one went by really fast there at that part. Let me stop there for a moment. Are there any questions about that before we move forward? I want to be sure that we're all on the same page here. So no questions so far? How'd I get the -6? I did A times C there, Brian. So I used the AC method. So to get -6 here, I have to take the 3, multiply that by the -2. Yep. So that's the first step as part of the AC method. Have to take A times C. Okay. Yeah, so don't forget your factoring methods that you have to use. All right, I'm using the AC method in this particular instance. Maybe I use quadratic formula, maybe I use whatever, okay? Again, it just depends what method is going to be easiest to solve for x, but that's what we have to do, so we don't have much of a choice in the matter. Okay. Any other questions? Any other questions before we move forward? I don't want to make sure here. How did 1x minus 2 become 1x plus 2? Okay, So the key there, Lyserna, is that what we did here is we took, because we brought down this negative down here, you actually factor out a 1, but you actually didn't factor out a 1, you factored out a -1. So these signs have to flip from a minus to a plus x and from a -2 to a +2. So that's why we got, because of this minus sign that was brought down here, Lyserna, that's exactly why this became x plus 2 instead of x minus 2. Okay, so don't, be very careful about that. Yeah, don't forget that was something we talked about before. That minus sign that drops down is very important. Okay, remember that does indeed change the signs. Okay, so got to be really extra careful. Put a note there, put something in your notes so that way you don't forget. I don't disagree that happens to be something that'll trip up a lot of people. So any other questions before we move forward? Anything else? We'll move on to the next part. Nope. Okay. All right. So now we found our two x values here of 1/3 and -2. All right. Now let's go to step number 4. Now step number 4 is where the visualization really starts to happen. Okay. So step 4 says chop up the number line using the zeros you found in step number 3 and determine your intervals to test over. Okay. So we're going to take a number line here, just a number line. So from -infinity to -infinity, that sort of number line. Put that in black here. Now, I'm going to take our two x values here. We have -2 here, and we have +1/3 here. Okay, now what it's going to be determined is it's going to be determined if we're going to put brackets or parentheses here. Now, of course, with negative and positive infinity, there's always parentheses there, so that part is kind of Mr. Automatic. All right, actually, let me put this here. No, I take it back. Let's put parentheses there. All right. However, at -2 and 1/3, how do we know to put brackets or parentheses? Well, I added this note here. We're going to use brackets for less than or equal to or bigger than or equal to from the original inequality after step 1, or parentheses for strictly less than or strictly bigger than. Now, in this particular example, if we go back to step 1, we have specifically here what I want to clue in on is the inequality itself, which was, in this case here, less than or equal to. Okay, so because this was less than or equal to, all right, then in this case here, we're going to put brackets. Okay, so we're going to put brackets around -2 and 1/3. So we'll put bracket here, put a bracket here, put a bracket here, put a bracket here. Okay, all right. So as you can see here, we have 3 intervals. Okay, so let's list those 3 intervals here. We're going to make a little chart here actually for step 5. So let's at least make the beginning part of that chart here using this chopped up number line that we have here. So what I'm going to have here is I'm going to have here first, I'm going to have an interval. So I have 3 intervals here. I have from -infinity to -2. I'm going to have -2 to +1/3 bracket. there in the bracket here for 1/3 to positive infinity. This will be the first part of my little table here that I need for solving for this inequality. Now you'll see what else I need to put into this little table here in just a second. But we have those three guys for our intervals. Now, in the next step here, step 5, is we need to take a test point in each interval and plug it into the polynomial in step 1. All right? We're going to determine if the answer is positive or negative. That's all we care about. So let's go ahead and do that here. So if we take a test point here, and we're going to showcase this in just a second. And the only thing we care about here is if the answer is positive or negative. I don't actually care what the number is. I only care about if it's positive or negative, all right? So basically, if you think about it this way, it's like saying, all right, even if it's 16, who cares? If it's plus, it's plus. If it's minus 16, it's minus. Okay, fine. That's all we generally care about. But before we actually get to that point, we first need to take some test points here. All right, so we need to take some values inside each of these intervals. So I'll have you guys choose for me here. Let's pick a test point here between negative infinity and negative 2. What's a value between negative infinity and negative 2? All right, negative 6. Sounds fine with me. Let's pick a test point here between negative 2 and a third. So negative 2 and 1/3. What's a test value we can choose there? Negative 1. Seems fair. All right, and let's pick a value here from 1/3 to infinity. Any value here that between 1/3 of infinity. 1, 9. Yeah. Either way, you can pick 1. You could pick 9. Okay, I'll pick 9. I'll pick 9 since Brian had one already. So no offense, Brian, you had. All right, so we'll pick 9. All right, so what do we do here? We want to just plug this in to the original polynomial. So this 3x squared plus 5x minus 2. That's all we're going to do. You can take out your calculator for this, and that's fine. You can plug this in. So 3x squared, let's go ahead and put this here. 3x squared plus 5x minus 2. Okay. Okay, and so all we want to do here is just take a look at these test points here. So if you want, you just take a look here, go to second and graph. Oh, I guess we already have these from our yesterday here. So let me delete these out, sorry. And I guess because we have it as an ask, we could go ahead and plug in negative 6. And we get a positive 76. So again, at negative 6, we get plus. Okay. Now we try minus 1. All right, we get a negative number. We'll try 9. All right, we get a positive number. Okay. So this is our little table that we have here. We found our intervals after chopping up the number line. We took some test points here, and we found if again it's positive or negative, just taking a random test point. Okay. Questions so far? We have one more step to do. I want to be sure everybody's on this page though here. Any questions about this step? If we put u's between the intervals, would this be also in if we put u's in between the intervals, would this be also in the domain? The domain again is just basically whatever works, right? So don't mistake the domain here, Jess. What we're looking for here specifically is just one or two intervals here, or all intervals that are going to satisfy the initial inequality. So if you have 2 or more intervals, you could put a u in between them. That part is true, if that's your question. all right, if for your final answer. But we haven't found our final answer here just yet, Jess. We actually have one more step to get to our final answer. So we can't make the assumption just yet that we have our final result. But the domain is going to be a separate entity here, at least as a concept compared to what we're doing here, which is to seeing what intervals satisfy our inequality. Okay. Okay. So in this particular instance, let's look at the final answer. What is the final answer here? So step 6 acknowledges what this final answer is going to be, because it is going to be some intervals here. Your final answer will be the intervals that follow the original inequality from step 1. Now let's take a look at the original inequality. The original inequality here, I'm going to make this bigger now. The original inequality in this instance, I'm going to zoom out here. Notice the original inequality here talks about less than or equal to 0, meaning to say we need to find the interval that makes it negative because it is less than or equal to 0 according to what we have here from step number 1. So our final answer is going to be, what is our final answer? Our final answer here, actually I'll put final answer for equals. Wow, how did that not register? Anyway. So our final answer here is going to be specifically the interval that is going to be our winner is going to be this one right here, which is going to be -2, comma 1/3. Again, because that interval had negative as its result from our test point, and we want it to be less than or equal to 0. Are there any questions about how we determined which one of the intervals was our final answer? Well, you just plug in -1 there, Stephen. We chose -1 as our test point. It was a value in between -2 and 1/3. If you plug in -1 into your original function, you're going to get a negative value. So that's all you're doing there. You don't care what the number is. You only care about the sign of that number. That's the most important point. The sign of the number takes precedence here. Any other questions before we move on? No? Okay. All right. Now that you have this example, do we choose the point? Hang on. Did we choose that point because it's included? All I did was choose the test point here that's inside the interval. So you could literally choose any number that's at least inside each one of the intervals there, Jess. So you don't have to guess like what point you want to choose. You can choose anything as long as it's inside the interval as a test point. You don't have to be like super choosy. If you say, hey, I want to pick 9 because it's between 1/3 and infinity, go ahead and pick 9. That's fine. Thank you for the hydrate, Josie. Okay. All right, anything else before we get to this next example here? Got a little bit more to do. I guarantee that. All right. All right. So I want you to think about this. Oh, yes. Go ahead, Fritz. How do we know that would be our final answer? Again, Fritz, go back to what we say here. Again, Fritz, you see it's less than or equal to 0. So that means that you want the result here to be negative if we're talking about less than or equal to 0. So that's why I know this interval is going to be our winner, because when we tried out our test point, it turned out to be negative, which from our original inequality is what it asked for. If that one said it was bigger than or equal to 0, I would have picked the first and the third intervals instead. So that's essentially how we can know that that's going to be our final answer. All right, I do got to move on here to the next example here, because I got to showcase at least another one here. Not the same type, but I want you to use this example as a backdrop for what we're going to be doing next here, which is this is the polynomial case, okay? But we also got to look at the rational function case, okay? So we're going to come up with another example here, and we're going to at least do that as well. So we have the polynomial case, but we also need to do the same thing here for rational functions in pretty much the same vein. So you'll see what I have written here for the notes, and then you'll see how that's going to work out. So, all right. All right. So I'm going to point this out here for number 10. Okay, so number 10 here says, how do we solve for rational inequalities? Now, I kind of paraphrased here for just a second. We'll look at that example. It says the steps here are the same as polynomials, but with a change, just one change. We're going to change the inequalities to equals. We're going to find all the values that make the denominator equal to 0. We're going to find all the values that make the numerator equal to 0. And then we're just going to follow the steps 4 to 6 from the previous question. Okay, so we're going to do a few things here. I'm going to put one more note to this here, but let me at least start the example here first and foremost, and then we'll see exactly how things work out. So, all right, so I want to do a little bit of a tougher one here because again, the first part of the function can be a little bit daunting. So let's do that. I'm going to modify this just a little bit. Okay, there we go. All right. Okay, so here we get x plus 1 over x plus 3 is less than or equal to 2. Okay, so what we need to do first is pretty much the same exact thing that we did here last time, all right, and in the last example, and that is we want to get in step 1, we're just going to try and move everything over to one side so we have 0 on one side and we got everything over on the other. So I'm just going to subtract 2 on both sides here. So what I'm going to get here specifically as x minus 1 over x plus 3 minus 2 is less than or equal to 0. Now, the biggest issue about this is that I don't want to actually leave it as just the minus 2 out there sitting out in the middle of space. I am going to go ahead and simplify this here because for what we want to do is finding zeros and doing all that stuff. We want to kind of combine everything together. So I'm going to multiply by x plus 3 on the numerator and denominator for a common denominator. So if I do x plus 1 minus 2 times x plus 3, and I put that all over x plus 3. That's why I multiplied by x plus 3 over x plus 3. So at this moment, I'm just simplifying down the left-hand side. That's why I'm doing this on purpose, because can be tricky if you're not aware. So distributing the 2 here, the next step, I have minus 2x minus 6 Okay. And then I'll just combine my like terms here. So I have minus x, 1 minus 6 is minus 5 over x plus 3 less than or equal to 0. Okay, so this is what I'm going to start off with. I have minus x minus 5 over x plus 3 is less than or equal to 0. Okay, seems fair. Now, what do I have to do next here? Well, I'm going to take the same approach that I did in the last problem, kind of. Okay? Now, what I'm going to do here next is I'm going to find my zeros of my polynomial, but I'm going to do it in two separate parts. You're probably wondering exactly how does that happen and why am I doing that way? Well, let's take a look at I'm going to look at the denominator here first. So I'm going to take a look at the denominator here according to the notes. So the note here going back, we're going to find the values that make the denominator equal to 0. Okay, now why am I doing this? Well, for one specific reason. If I set this equal to 0, very simple, I get x is equal to negative 3. Remember here, this is something that we did with piecewise functions as well. Remember, if this is equal to 0 here in the denominator, we want to exclude that value. So go ahead and make a side note here is that you are going to exclude. All right? You're going to exclude that value because obviously we don't want to divide by 0. So remember, anytime we exclude here, if it helps, go ahead and say you're going to put a parenthesis next to that negative 3. Okay, so that's going to be part of it. We're going to use parentheses here next to negative 3. All right? That is going to be very important as part of the process here. All right? So remember, in the last example, we did brackets because it was less than or equal to, but in this case here, we exclude because negative 3 makes the denominator 0, so that's pretty bad. Don't want that. In the other one here, we have minus x minus 5. We're going to set that equal to 0, so that'll be its own separate thing, the numerator. Be very careful about this, by the way. I'm actually going to do this out as algebra. So I get minus x equals positive 5. I divide by negative 1. So I have x is equal to negative 5. Now, just to give yourself a reminder here, if we look back at our original inequality, this says it's less than or equal to. So again, if you want to put the word include next to that and put some brackets, so that way you give yourself a reminder, said, hey, I need to put brackets next to that particular number, go ahead and do so. Maybe that'll make it a little bit easier. Again, you'll have the visual representation that you'll know parentheses go this and brackets go. Again, this can be included because of this, because of the inequality. So I'll just put here because of less than or equal to. Okay. All right. Why did I put it there? Anyway, okay. So that's what we have there for those couple of steps. I did want to at least showcase that out here really quick about what we want to do there in that case. Is really with step 2, step 3 is really, I guess I should have put this equal to 0, but you get the general idea. So I guess I should mark this as step 3 instead of step 2. My fault. Step 2 should have been this. Minus x minus 5. X. Sorry, it should have looked like this. My fault on that. My bad. I accidentally skipped step 2. I just went straight to solving for x. Okay. All right. Now, before I move to step 4 here, are there any questions about these first 3 steps? Any questions at all about these first 3 steps before we do that? Before we do the table stuff? No, okay. Well, let's move to step 4 then. Okay, all good? All good. All right, let's move to step 4 then. We're going to make our number line. So start off with negative infinity, go to positive infinity. We're going to have our two numbers here of -5 and -3. So again, we know that at the infinities, we're going to have parentheses. That part is always true. -5, we're going to put the brackets there. We want to include that. We're going to have brackets there. -3, we're going to have parentheses because, again, we want to exclude that value. So we have here, as you can see here, we have three, once again, three intervals. Let's make our little table. We have our interval here. So we have from negative infinity to -5, bracket. We have bracket -5 to -3 with the parenthesis. We have parenthesis -3 and positive infinity with parentheses. All right. Okay. So let's take a test point in each interval. Why don't you guys give me these numbers here once again? What's a good test point here we can choose for that first interval? Negative infinity to -5. It's a good test point to use there. All right, -10 sounds fine to me. Then terrific. All right, how about -5 to -3? A good test point in between those two guys. Yep, -4. Pretty solid. Pick one more. -3 to infinity. What's a good test point to pick between those two guys? Any number there? 8. All right, 8 works. Okay, so we got our test points here, each of them in their respective intervals. 8 and 5, and you can pick 5, you can pick 8, you can pick any number you want. Now, what we have here specifically is we have plus or minus. That's what we want to do. So we're going to take out our calculator here. We're going to figure out what we have here in terms of plus or minus based on our test points. Let's do that right now. Again, remember to use your original function here that you have from step 1. So again, -x minus 5 over x plus 3. So that's what we're going to do here on the calculator. I'm going to put -x minus 5 over x plus 3. Those in parentheses. And we're going to go to the table here. We'll hit second in the table, and we'll just go ahead and enter in these values here. See what we get. All right. So let's take our test points here. Let's plug them in, see what we get. So let's try -10. All right, so that's a negative number. Okay. Let's try -4. All right, so that's a positive number. And let's try 8. Okay, and that's a negative number. All right. So we got the first one here negative, second one positive, last one is negative. Okay, good. So we found our 3 guys here for part of our table. That'll take care of the calculator part. So now all we're going to do here specifically is I'm zooming out. So we want to get to our final answer here. So let's take a look here. I know this is a little bit tough to see, but what is our final answer? What interval or intervals are going to be our final answer here for this problem? First, second, or third. Tell me which of those interval or intervals are going to be our final answer for this problem. So that's the question here. Tell me, from our intervals, the first, second, or third, what is our final answer? Okay, very good. The first and the third. That is correct. So our two winners here are going to be the first one because it's negative, and the third one because it's negative. That's right. Good. Because it said, again, at the very outset of the problem, we had less than or equal to 0. Because we had less than or equal to 0, we're forced to have this, okay? We have to use the negative value here, okay? All right. So having that here, our final answer here, finally, is going to be negative infinity, negative 5. Put the little u guy there. Negative 3 to infinity. Let me see here. These problems will always be equal to 0. You're going to set it up that way. So, Brian, that's why I've set it up that way. Every one of these problems here will be set up that specific way. You always want to make them 0. So again, follow the original inequality, right? Again, it'll just be based on the original inequality, but that's why I put step 2. Step 2 here, we change the inequality to equal 0 and then start solving for x's around that. So you always want to put it in that context, and then once you're done solving for x there, Brian, then you're going to come back and use the inequality here to see if you got brackets and parentheses and whatnot. So the one thing I'm going to add here specifically, actually in relation to your question there, is going to be this. Wait, okay, so not for this problem because, okay, look, Brian, if this was bigger than or equal to 0, then I would look at the second one, right? So you're making again, you have to look at it a case-by-case basis, all right? If this case said less than or equal to 0, then you're looking at the negative answers. If this said bigger than or equal to 0, you're looking at the positive answers. Yeah, don't get stuck in the mindset that it's going to be just one way all the time. You got to look at it a case-by-case basis and then try and do the same general steps to arrive at a result. I understand. That's why I'm trying to move you away from that mindset. Because that's how you struggle at math, is like you always think that a problem is always going to go one way when you're forgetting that you're trying to do the same general steps, but you have to still look at it a case-by-case basis. That's why they're like, if it was that way, then we could have all the same problem all the time. So real quick, why is minus 3 not included? Because minus 3 we got here from the denominator. Minus 3 came from the denominator here, Fritz. That's why. Actually, I'm going to put a note to that here. That was the next thing I want to talk about here. So note here, always exclude, again, parentheses, always exclude any answer you get, from setting denominator equal to 0. Okay. All right. So I was going to make that as kind of a note there, so that way you can see what the story is about that. That will always happen for the denominator, by the way. So you're always going to exclude because you don't want to divide by 0. So I just wanted to make that note there to answer your question there, Fritz. All right. Cool. All right. Any other questions? Any other questions? Okay. So that'll effectively, pretty much, that is effectively the synopsis here for section 3.6. No, this was 3.5 and 3.6, Nicholas. So this was both sections. We actually got both sections done today. So the only thing that we're going to do here is we're going to continue with this handout from last time because I have 3.7. That's the last section we need to do from here. And then we're going to transition into chapter 4. So that is what the plan is for tomorrow. All right. All right. All right. All right, ladies and gentlemen, I've ran a little bit overtime here. I do apologize. Okay. All right. I want to thank everybody here once again for coming on out here to the stream. All right. I love you all here. Again, if you have questions, then again, I'm going to be on Discord here or on email. All right. Yeah, we're going to meet back here same time, same place tomorrow. Okay. As always, that's the plan. All right. All right. Okay. See you tomorrow. All right, everybody. I will see you all tomorrow. And as always, ladies and gentlemen, as always, as I like to say here, stay safe, stay healthy, but most importantly, stay sane. All right. Have yourself a wonderful day / afternoon / night. All right. We'll see you here, same time, same place. We're going to get some more stuff done. Great job, everybody, here today. Everybody, take care of yourselves. Have a great one. See you later. Bye. Bye.